So first of all, we'll see the definition of greatest integer function. It is defined in piecewise form when x, let us say, lying between -1 and 0, the -1 is closed, 0 is open, then the value of the greatest integer function will be -1. When I substitute the value between 0 and 1, the function will provide us 0. When I substitute the value between 1 and 2, including 1, the function will provide the value 1, and so on. So it means that suppose I have a number lying between two consecutive integers. Suppose I have I is there and I'm taking I plus 1 is there and I minus 1 is on the left to the I, and I'm taking a number lying between I to I plus 1. The value of the greatest integer of that number is going to be I. It means wherever you go from starting from I and till I plus 1, the value of the number is going to give you the I. So for example, suppose I take the greatest integer of 3.9, that must give you 3, or you take 3.8, that will also give you 3, and so on. In the negative side also, suppose I have minus 3.9. So below minus 3.9, we have plenty of integers. Among those plenty of integers, which is the greatest one? That is minus 4. So that is minus 4. So we can say in words, the greatest integer is the greatest of all the integers below x. That's it. And this is actually making sense because when I'm taking, let's say, minus 4.3, so below minus 4.3, I have plenty of integers. Among them, the minus 5 is the greatest one. And so the value of the greatest integer minus 4.3 is minus 5. And how we can graph it? So to draw the graph, we have to understand the definition in every such interval, and we have to keep drawing it. So between 0 and 1, if I have any number, so x is lying between 0 and 1, let us say, the greatest integer value will be 0. So when we are going from 0 to 1, I have to be on the same height because the value is 0 only. It means from 0 to 1, I have this graph, but 1 is not taken. Again, we go from 1 to 2, the height will increase because between 1 and 2, if you take any x, the greatest integer will give you 1. So for 1 and 2, this is 1 there. So between 1 and 2, I have to maintain the height of 1. And again at 2, the value will jump off to 2. So between 2 and 3, the height will be maintained at 2. And again at 3, it will jump off at 3, and so on. So in this way, we can create a staircase kind of a structure. That is why it is also called a step function. And it is also known as the floor function. So step function is also one name of the greatest integer function. And the floor function is also another name. So these are, by the way, the fancy names, not so much mathematical name of it. All right. Now we'll try to understand whenever we are applying the greatest integer to a given function, how the graph will look like. And the aim of the video is to solve some questions graphically in which the greatest integer function is involved. So let us say I have a function fx is equal to x squared. And from there, I want to draw the graph of a new function gx, which is the greatest integer of x squared. So how we can draw it? Let me first draw the axis. So let's say I have these two axes here. So we'll start from drawing the graph of x square. So the graph of x square, you know, this is at 1, this is 1. At -1, this is again 1, and so on. And the graph of x square is an upside open parabola. So at 2, this will shoot up to 4. So 1, 2, 3, 4. So it will hit there. And similarly, at -2, it should get to 1, 2, 3, and 4. So it should go there. So this is the graph, a kind of schematic diagram for the x square. Now to draw the graph of the box of x square, we have to think in this way. This box will give you the value. Whatever you take the value for x, it will always provide you integers. It means it can provide you 0, it can provide you 1, it can provide you 2, and the negative side it can provide you -1, then -2, and so on. So we have to think from where to where the value should be 0. So it's not so difficult. Suppose I'm taking x square from 0 to 1, then only the box of x square will give you the 0. It means I'm going on the y-axis from 0 to 1, and I'm just taking the horizontal line there, and I will read off the value just one step below that integer. I mean to say that, let me just try to convince you by this way. I'm going here, I read off the value, the horizontal line, and I can see that this is the piece I have for that entire part. I'm going to draw this part 0 to 1, and for that this piece is covered. So I'm taking the projection of that piece on just below integer. So for that 0 to 1, I'm taking this piece. So let me take this color. This is 1. And I will just stop here. Now I'm going again from 1 to 2. So from this 1 to 2 I'm going. So let me take it. This is 1 here. Let me just take a little bit. Okay. So this, let's say this is 1 here, this is 2, this is 3, and this is 4, and so on. So what I'm going to do now, I'm taking 1 to 2, and for this 1 to 2, I'm seeing this is the portion I have. For this portion, I will have the below integer, this one. It means I'm taking the portion, the projection of this portion on just below integer. It means I can mark it like that. I'm going from here to here, and I have this much portion I got for that, and this portion I'm taking the projection on the just below integer. So I got this portion. It means for integer, greatest integer, I got this graph and this graph. Again I'm going from 2 to 3. So for 2 to 3, if I see that I got this much portion, and for this much portion, again I identify that I'm getting this kind of picture. So in each integer on the y-axis, I am considering that portion of the graph and taking the image or the projection of the graph on the just below integer. And we have to do a similar process for the left hand side also. So this is going to be our portion there. Then we got here, by the way, this is there, and then we got here, and so on. In this way, we can draw the graph of greatest integer of x square. Let me take another example so that I can make this whole thing clear. And at this time I'm taking the scale a little bit larger so that you can see this thing clearly. So suppose we have this time the function fx is equal to x cubed, and I need to draw the graph of gx, which is the box of x cubed. So for that, I am going to draw the axis first. So this is the axis I have. And now I'm going to draw the graph of x cubed. So for 0, that is 0. At 1, that is 1. So the graph, well, let me just take the scale I promised larger. So I'm taking 1 there now. And then 2 there. -1 and -2. So at 1, that height is 1 there. And at 2, it will shoots up to 8. So let us take this 1, 2, 3, 4, 5, 6, 7, 8, 9. So let me just take it. At 2, I'm calling this value is 8. Just for the sake of convenience. And this side also, let me first draw this part. And this side also we have to do the similar process. So we have this kind of graph, this side also. Okay, so let's try. Now I am interested to find out the greatest integer part of, or greatest integer of x cube. So I will start from 0 and go up to the nearest integer, so 0 to 1. And for that, I'm reading off the graph. It means I'm taking that portion which is covered by 0 to 1. So I have covered this portion here for 0 to 1, and take the projection of this portion on the below nearest integer. So the projection we got as this. So I'm just taking a different color for the projection. So this projection we got, and of course at 1 it will not give you the value 1 here. So that. Now we go for the next portion. So for next portion from 1 to 2, I have this 1, this is 2. So I'm going again 1 to 2, and I'm reading off the portion which is covered by 1 to 2. So this is the new portion I have. For this portion, I have to have the projection on the just nearest below integer, and that integer is nothing but 1. So I have to take the value 1 from here to here only, and so on. So I have to identify what that value is, and it is not difficult to identify because this value must be 2 to the power 1 by 3. Then only it will become 2 there, and of course this is the integer of that. Now we go for next portion, so 2 to 3. So 2 to 3. So let's say this is 3 there. And of course 8 is not that much close, but you understand my point. So I just erased it. So this is 3 there, and now I am taking the portion, that is the portion here from 2 to 3, and for 2 to 3 I have this portion. I'm taking the projection at 2, and that is the greatest integer of that. And of course this value will be a larger than 2. Even if you are seeing this at 2, it's the fault of the human hand, that's it. So in this way we can plot this part also, and this is the way to find out the greatest integer graph of any function. Now, how do we apply this technique to solve some questions? Let's try. So this is the first question I have taken, and the question is that fx is equal to x by 2 minus log of x plus e root e, and gx is half box x, and we have to find the number of solutions of the equation fx is equal to gx, and so on. So let's first simplify the function fx. The function fx can you write as x by 2, and minus this log I can write as log x plus e, and this I can write base e, and this half I can take out. From there I can also simplify more, that is fx, and here going to be, I can write ln e divided by ln of x plus e. So I have now, this is simplified. So ln is 1, and this can be written as x by 2 minus 1 over ln x by. So this is the function we got in the simplest form as far as possible, and the gx is I have half of box x. Now we are equating them and seeing that what are the functions we need to draw the graph of. Let us just equate first. So I will write fx is equal to gx. So from there I'm getting the fx is x by 2 minus 1 by ln x plus e, and that is equal to half of greatest integer. In here what we can see that this is x by 2 minus half of box x is equal to 1 over ln x plus e. So from there what I'm getting is the x by 2, where this 1 by 2 went. I think there was 1 by 2, so I did a mistake there. That is 1 by 2 should be there. All right, so that's why I was thinking when I created the question why this 1 by 2 is not getting cancelled. So this is 1 by 2, and this 1 by 2, 1 by 2, 1 by 2 get cancelled. So I am left with x minus greatest integer and 1 by ln x plus e. All right. Now this x minus greatest integer is called the fraction part of x. What is the meaning of fraction part of x? Means any number is written as the sum of integer and some fraction. If the fraction is not there, that will be 0. So suppose I'm writing x, and x is the fraction part of, so integer part of x plus fraction part of x. So for example, let me take example right there first. So for example, if you see, I'm writing this 3.9, so I can say that it is composed of 3 and plus 0.9. It means 3 is the integer part and 0.9 is a fraction part of that number. So it means if I have no fraction part like 5, I can simply say it's an integer, and so the fraction part is 0. So that's why when I say that x minus integer, it means I'm left with the fraction part. This is the notation of the fraction part. This is fraction part of x. And now I have to see that for any x less than 0, is there any such solution for this fraction part of x is equal to 1 by ln x plus e is there or not? So how do we do that? We have to see. Let me first revise the fraction part for you. So you know that the fraction part for any x always lie between 0 and 1. Why so? Because when you take any number, it is composed of some integer and the fraction must be between 0 and 1. And this is 0 is included because when you take a complete integer, there is no fraction part at all. And the graph of the fraction part is always lying between 0 and 1. So let me draw the graph of it also, so that we will take this definition to solve that question. So I have this thing. Now, between 0 and 1, if you take any number for the fraction part, it will give you the value what we substitute. Why? Because when you are substituting here, let's say 0.1, and you are asking that what is the fraction part of 0.1, the answer is 0.1 only. It means that the value what you are substituting, you are getting the same, means the graph is exactly like y is equal to x, because from 0 to 1 whatever you are substituting you will get the same thing. Now from 1 to 2 if you move, suppose I am substituting 1.1, I'll get 0.1, or 1.2 I will get 0.2, or 1.3 I'm getting 0.3. It means again from 1 to 2 whatever value you are substituting, you are getting the similar height what we got previously in the previous interval. So I'm getting a similar kind of repetition of the graph, and so this graph will repeat like this in each integral interval. All right, here you can notice one important thing. When you take any negative value, suppose I'm taking, let me take this thing down. Suppose you want to find out the greatest, sorry, not the greatest, fraction part. So fraction part of minus 0.9, it will give you 1 minus fraction part of, 1 minus 0.9. So that will give you 0.1. And similarly, suppose I'm taking 0.1, that's why we're getting this height. You see that this is minus 0.1, so that the height is 0.9 and so on. So this is the definition and the graph of the fraction part of x, and I need to solve this equation in the light of it. So let's solve it. We are not solving completely, as you know, we are only finding out the number of solutions. So let us do it here. So now we try to solve it graphically. So first of all, on the left hand side we have the fraction part of x. So I'm drawing the graph of fraction part of x. It is lying between 0 and 1 as we saw earlier. So this is the line y is equal to 1, and 0 to 1 I have to draw the graph. So let's say this is 1 here, this is 2 here, then 3, and here this side also a similar kind of graph. All right, now this is minus 1, by the way, minus 2, minus 3, and so on. Now I have to draw the graph of 1 by log x plus e. Let's try to understand how do we draw the graph of log x plus e. So you know that the ln of x plus e, the log of x plus e, is not defined at minus e. Means any number, if you take lesser than minus e, the function is not defined. It means the function starts its graph from x equals to minus e. You can think in this way, that if I have to draw the graph of log x plus e, we are shifting the origin or the y-axis at minus e. It means the asymptote what we see at minus e is there, and here is minus e. Minus e is somewhere between minus 2 and minus 3, and there is one asymptote kind of thing. So let me draw it a different color. So this is our minus c. But you also notice one thing is a reciprocal. So suppose I have to draw the graph of reciprocal. So let me just give you the idea here. The log x graph is increasing. In order to draw the graph of reciprocal of it, from 0 to 1, I must have a decreasing thing. But at 1, the denominator will become 0 if I am drawing the graph of log x. In the same way, what will happen? When you substitute there, x equals to minus e plus 1, at that, the denominator will be 0 and the graph or the function is not defined. So minus e plus 1 is somewhere here. And there must be one more asymptote here. Like this. And when I say that any number, when I'm taking any number more than minus e plus 1, so let's try to figure it out. If you see that, if I substitute 0 in this place, x equals to 0, that will give you 1. It means it should come like this, and it should hit that 0, 1 on the y-axis. So this is 0, 1 on the y-axis. It means it should come in this way and go below. How I'm saying that is go below? Because you can see it will never pass the x-axis. It means the asymptote, the horizontal asymptote will be x-axis, because when we take x equals to very high, when x is infinity, it is going towards, the entire thing is going towards 0. So the graph will look like something like this when x is positive. One more important thing is here, this is not the intersection point. Why? Because this is a open interval there, or therefore the 1 is not taken. It means it will pass through this hole. What about the function below this negative e plus 1? So you can see that when I have negative e there, the value will become 0, because log 0 is not defined, so it will start a little bit ahead 0 here. And when we are substituting each number ahead of minus e till minus e plus 1, the value will be decreasing, and so on. Why it is decreasing? Because when you see that, I'm saying that when I substitute any number more than minus e in this log of x plus e, it should increase. So when you do the reciprocal of it, it should decrease. So we'll start just ahead of it, and it will go like this, I don't care, and it will approach towards negative infinity when I have minus e plus 1 from the left. But when I have a minus e plus 1 from the right, it will again start from the positive direction. It will go like this. And so this is the intersection points, what we can see here, here. You can see that the first intersection is happening between 0 and 1. The second intersection will happen between 1 and 2. And we are going from 0 to 10. So from 0 to 1 intersection, 1 to 2 second intersection, and so 9 to 10 will be the 10th intersection. Therefore, you can see that for x greater than 0, the number of solutions will be 10. For x less than 0, there is no solution, because the graph is starting from here and going down, and this is not intersected by any part of the fraction part of x. Therefore, the correct answer is, for the first part of the question, this is no solution, and for the second part of the answer, there are 10 solutions. There another way to draw this graph. I mean, we have already drawn the graph of this function like this. Fraction part of x and is equal to 1 by log x plus e. There's another way to think this entire thing. Let me just give you the idea. You notice that I have, let me just write another way. So in fact, I'm writing the original question, x minus greatest integer and 1 by ln of x plus c. I can also write the greatest integer on the left, and this I can write x minus 1 by ln x plus c. My point is, here I'm going to solve this by drawing the graph of greatest integer and the graph of this. It's difficult to draw the graph of x minus 1 by ln x plus c, but schematically we can understand how the graph will look like, and we can reach the solution. So let's first try to draw the graph of box X, and you know that I'm drawing the graph of box X like this. This is one step, second step is here, the third step is here, fourth step is here, and so on. The same way I have this, and so on. Okay, now I have to mark those points. So there is 1, there is 2, 3, there is 4. Similarly, this is -1, and this is -2. This is 0, and this is the graph of greatest integer. So left side is already done. Now what I'm doing the right hand side. For that, let me just bring it a little bit left. All right. So here I have to think about this x minus 1 over ln x plus c. Let's try to think. You can see that whatever with the value you substitute for x greater than 0, I'm saying, for x positive, this quantity is always positive, because you are adding e and it's a positive quantity, it's always positive. And whatever the number we have for this, you are subtracting from x. It means this entire thing will be lesser than x for x greater than 0. And where is this x? So let me draw the line x. So this is a line. I have y is equal to x. It means that whenever x is greater than 0, this, let's say this is a function fx. So this function fx is always lesser than x. It means the graph will always be below this black line for y is equal to x. We have already done. And when I have this thing ln of x plus e, you can see that for at x equals to 0, this value is 1. Log is 1. It means I can say that the ln of x plus e is greater than 1, and when I have reciprocal of it, 1 by ln x plus e is lesser than 1. When you take a minus sign, the sign of inequality will get reversed, and when I add x, I will have x minus 1 by ln x plus e is greater than x minus 1. So for any x greater than 0, this is true. So what we are getting from this relation and this relation is the fx is lying between x and x minus 1. It means it is below x and above x minus 1. So let's draw the line x minus 1 there. So the x minus 1 is the line passing through 1, 0 on the x-axis, and it has the same slope, so it will be a parallel line which is passing through all these holes of the greatest integer we drew. So this line is y is equal to x minus 1. Now the value of this function fx, the fx, if you remember, we have assumed this thing x by 1 by ln x minus 1 by ln x plus c. So at 0, what is the value of this function? You can see that when I substitute 0, that will become ln e with a minus sign, so that is minus 1. So means at 0, the value of the function is here, it is passing through that, and below that, below any number which is less than 0, that whole quantity will become negative, because this is negative already, and I have a number which is, we are subtracting from this minus x, and this number is positive for any x less than 0, because we are not going beyond minus e. So we are talking about only the values which is lying between sorry, after minus e. So any value what you take here to substitute, which is less than 0, it is lesser than the e value. So of course this will become positive when you are, this is already x negative, so whole thing will become negative. So the graph should pass through this point and it will go like this, because after, when x goes positive, the graph has to have lie between x and the x minus 1. So it will go like this and it will never come, it doesn't matter how the graph you will draw in this two ladder kind of structure, and it will always pass through these integer points, but it will never come below x minus 1 or go beyond y is equal to x. So let us draw this graph in this way. So our graph must look like this, and the asymptote, if you are talking about, this was already minus e, and if you add minus e plus 1, so this is the asymptote. From there I have to start the graph for that. So let me draw it like this, and from here it will start and it will go like this, and it will go always forever. You can wonder that why I'm not drawing this graph in this way. So for that we have to see that it has to pass through this point. So it will pass like this, and it will pass like this, and the graph is always increasing. So again I have to come like this to go like to pass through the 0 comma minus 1 also. They're not possible because the graph is increasing. If you want to check, you can substitute the value x equals to minus 1 there, and you see that this function value will be always below this number. The other part of the graph we can also draw, but is not important because it will never hit this point. How we can see that? Because when you substitute x equals to minus e, this is not defined there. So again the graph will start somewhere from here, and as soon as we go at minus e plus 1, it has to be increasing, and it will go above, and it will be the asymptote with this red line. So in this way we can also see that every integer part of the function, greatest integer, is intersected by this curve, and so from 0 to 10 there are 10 solutions. This is another way to solve that question. I'm not saying that we cannot solve it analytically, but I'm only giving you the graphical understanding. In worst scenario, you can draw the graph and you can also solve it. Let's try to solve this question now. A similar one, and I hope you are understanding how to draw the graph schematically without using calculus and everything. So I have the greatest integer again here, and find the number of solutions between 0 and 20. So let's first call this function fx as x cubed by x squared plus 1. So we can apply calculus to think that whether the function is increasing or decreasing. So you can think by differentiating also. So f dash x and so on. So f dash x will become always positive. Let's try to figure it out. X squared plus 1 the whole square, x squared plus 1, 3x squared minus x cubed and 2x. So I'll give you 3x to the power 4 plus 3x squared minus 2x to the power 4. You can see that each quantity what we have encountered with all are positive. So this is always positive, I can say. It means the function is always increasing function, the x cubed by x squared plus 1. And we have to encounter that function with greatest integer. So again we draw the graph of greatest integer first, and we try to draw the graph of the x cubed by x squared plus 1 on the same plot, and we'll count how many points they are intersecting each other. So I have the greatest integer as usual. 0 to 1 I'm taking first. So 0 to 1 I'm taking this much length. Again 1 to 2, 2 to 3, 3 to 4, and so on the back also. Now I have to draw the x cube by x square plus 1 schematically. So I have fx is equal to x cube by x square plus 1. You notice when x equals to 0, I have the value of the function 0. So that's not a problem. Now you see how the graph will behave. So for that, let's try to understand how it will be acting between these two lines, what we drew for the previous function also. So I'm drawing the line y is equal to x first, and we try to analyze how it's the function behavior in these two parts. And this is our x minus 1. This is our y is equal to x, and this is our x minus 1. Okay, now I have to see that how it is related to y is equal to x, how we can think it. Let's try. So I have this x cubed by x squared plus 1. So for x greater than 0, let's first think. For x greater than 0, I can say that the x cube is lesser than x cube plus x. And why I'm doing this thing, because you want to make this function here, and you can understand the trick what I'm applying here. Because for any number x greater than 0, you're adding this x cube on the right hand side. So of course it will be higher than x cube itself. So I can say that x cube is lesser than, I'm taking x common from here. That is what? X squared plus 1. So I can write it x cubed by x squared plus 1 is lesser than x. So for any x positive, the x cube will be always lesser than x. It means it will be always lying below the line y is equal to x. Now how do we convince ourselves if it is there, whether it is always above x minus 1? So this is for sure that the graph will always lie below this line, below this y is equal to x line. The graph will always, and it will increasing, so it may increase, it's always below. But how do we know that it will not come below this x minus 1? If it is so, then we can easily count the number of integer points, or count the number of solutions. Not the integer points, the number of solutions we can count. So for that, we have to confirm that it will be above x minus 1, and it is actually tempting to be like that. So how do we confirm? Let's see. I need to understand that it is lesser than, greater than x minus 1. So let's think this way. For x greater than 0, again, suppose I'm thinking that x squared minus x plus 1, it will be always positive. How I'm thinking this thing? Because the discriminant of this quantity is lesser than 0. And so this whole quantity will lie above the x-axis as a quadratic, and so it will be always positive. Now what I can see that if I multiply minus sign, this will get reverse. So this time the negative x squared plus x minus 1 is lesser than 0. Now I'm adding x cube both sides. If I add x cube both sides, I will have this scenario. And so I'm getting something interesting. From the first two terms from here, I can take x squared common. So I'll get x minus 1. And again, I can take 1 common from the last two terms. And again I can take x minus 1 common, so I'm getting x squared plus 1 here. And you can notice now it is easy that x squared plus 1 I can send on the right hand side. And so I can say that x minus 1 is lesser than x cubed by x squared plus 1. It means we knew that now when x is positive, x cubed by x squared plus 1 will be always higher than x minus 1. So on the positive direction of the x-axis, I have the graph always lying between x and x minus 1. There is no such problem now. So this is the graph. We can easily see that it is going like this. But what about for the x less than 0? For x less than 0, what we can see? We have already done one inequality here. Let's try to reverse that inequality. So when I have x lesser than 0, I can do the same thing. Because when x less than 0, you can see that the x cubed will be lesser than x cubed plus x. X cubed will be greater than, x cubed plus x. How I know that? Let's try. Suppose I'm taking a number minus 2. So minus 2 to the power 3 is minus 8. And here minus 2 to the power 3 is minus 8 and minus 2. So you have already some value there with a negative. And you are again subtracting some quantity from that negative value. It means it will be lesser than this x cube. It's not that much difficult to understand. And after this, again, I'm doing the same process. So what I'm getting it here is x cubed greater than x common x squared plus 1. So x cubed by x squared plus 1 is greater than x. So now the work is over because we already understood that it's always above the x-axis. So the cubic graph will go like this. It will never touch or intersect this y is equal to x, not the x-axis. I think is a y is equal to x line, not the x-axis. It will be always above the y is equal to x line and it will never be intersected. It means for x less than 0, there is no solution of this function or this equation. But for x greater than 0, there are infinite solutions. But we have to count the number of solutions between 0 and 20. And you can think that the first solution is happening between 1 and 2. Here there is a one catch here. Between 0, because here the 0 is not included. So first solution we count from 1. And we are going till 20. So if you reach this 20, you will never find the solution because after 20, the solution will happen in the range of 20 to 21. So I have number of solutions is 19. All right, let's do the last question of this video. So I have this question. This is 2x minus 1. This is a very classical question for the greatest integer function or the greatest integer implication. So here the question is, the left hand side is the mod of 2x minus 1 and the right hand side is this thing, and we have to find the number of solutions of it. How do we solve it? Let's try. When I see this thing, we can do two ways. The first is either I can actually convert this greatest integer into the fraction part, or we can convert this fraction part in the greatest integer. So let me do the second one, and the first part or the first method you can try. So I'm going to write the 2x minus 1 mod, and this I'm doing the 3 box x, and writing this thing as x minus box x. Box x. So this will give you 3 box x and minus 2 box x and plus 2x. So we can get here the box x and plus 2x. and that is equal to the 2x minus 1 mod. We have to find the solution actually. We don't have to find the number of solutions, we have to find the exact solution. So what I'm going to do is I'm going to draw the graph of the mod of 2x minus 1 and this box x plus 2x. Let's see. So first of all, we draw the graph of mod of 2x minus 1. That is the v-shaped graph at somewhere at half. So I'm calling this value as half. So this value is half I have, and I want to draw the mod x. So when x equals to 0 on the y-axis, that will give you 1. So it should hit 1 there on the y-axis, and symmetrically it has to go at 1 also at the same height. If you say put 1 there, it will get the same height. So it will go like this and like this. So this is the graph of y is equal to mod of 2x minus 1 on the left hand side. Now we have to draw the graph of y is equal to the box x plus 2x, and we draw it very systematically and wisely actually. So 0, this is 1 there, this is 2 there, this is 3 there, and so on here also. Now you see that this box x is producing always the integer value. So let's find out the graph between 0 and 1. When x is lying between 0 and 1, our function will be turning into 2x plus 1, because the box x will produce the value, sorry, not 2x plus 1, 2x, sorry. The boxes will produce the value 0 only when x is lying between 0 and 1. So the box x is 0. So y is equal to 2x is the line we have. So from 0 to 1, I have to pretend that I'm drawing the graph of y is equal to 2x. So you see that for this part of this graph, for 0 to 1, I'm only drawing the line y is equal to 2x. So when x is 0, that is 0. When x is 1, that is going to be 2. It means I have this value at 1, that is 1 only. So this is 1. But at 1, it should give you the value 2. It means the line will look like this. This is the line we drew, and that line is giving you 2x from 0 to 1. Now we go for x lying between 1 and 2. So for 1 and 2, the line is y is equal to 2x plus 1, because the box x will produce the value 1 and 2x is 2x only. So for 1 to 2, it means in this branch, I have to draw the line y is equal to 2x plus 1. So we can draw in this way. There's no such problem. At 1, you can see that the value of this function at 1 is 3. It will start from, this is already I had the value 2. So let's start from 3. So it will go somewhere here. And after that, it has to maintain the slope of 2. And it will hit at 2 the value 5. So at 1, this will become 3. And at 2, this will become 5. So it will maintain the same slope of 2, and it will go like that. And similarly, in the next interval, it will happen something like this. So you can see that this branch had the slope 2, and you can see after that the line is maintaining every time the slope 2. So these two lines will become parallel in each of such graph what we draw for the next part of the integer, means the next interval of the integer. So for 2 to 3, again this will become 2x plus 2. So it will start from somewhere here, but will maintain the same slope which is parallel to this branch of the mod 2x minus 1. So it will never be intersected after this intersection. So there's only one intersection is happening here. You can also feel that below this part also the graph will be looking like that only. So there's no intersection anymore. So the only intersection point we can see in this interval between 0 and 1. So between 0 and 1, this is the intersection, and you can see that this line, I have the slope minus 2x, because this is the, if you see the mod x graph, the left part is minus slope and the right part the same slope. So this is minus 2x and is passing through 1. So this line is y is equal to minus 2x plus 1. And this line we have already drawn, that is 2x. So we can simply solve them together and we get the answer. So I have minus 2x plus 1 is equal to 2x. Therefore 4x is equal to 1. So x equals to 1 by 4. And that is the answer. That's it for today. See you in the next video. And in the next video, we will do some more exploration of the graph. And the particular function is the reciprocal function. So we'll see some rational function and also some other questions. So till then, stay math active.